present Capstone Project Part B. Our project is Plastic Heat Point Carrier Project. Our team has 3 members, Sebastian Skoltos, Sarita Paisan Satichon, and me, Gapya Mingson. Let's start now. In general, heat pipes are connected with heat sink for taking heat out from device in order to prevent overheating and failure of device. A carrier is constructed for support heat pipe. In the market, the carrier is generally made from metal materials, mostly be aluminum, which contain high heat transfer coefficients, but it has heavy weight. Plastic, which is lighter, could be used to producing carrier instead of aluminum. So our purpose of this project is to test the behavior and vulnerability of the plastic heat pipe carrier for a standard Victor heat pipe. We will utilize the law of thermodynamics on Excel calculations, use ANSYS computer program for analysis, and conduct physical testing in the thermal laboratory of RMIT. The challenge of this project is on physical experiment. To complete this, we need to design testing setup, construction of a testing rig, experiment parts and tools. Calibration of equipment is necessary in order to ensure that the physical testing is going to the correct way. Also, throughout the result were used, they were far more inaccurate when capturing temperature data from the dynamic testing, as the acrylics was used on the test section. This being asked to change the design in last minute. Moreover, the components of testing need to be shared. We share power supply, data taker, and copper heat block with electric isolations of heat pipe group. Despite we both groups have a good communications, but we still face with overlap on schedule. Next, Sebastian will explain how we conduct this project.
Hi, my name is Sebastian and I'll be covering the group's aims for testing and testing methodology for the semester. Making use of RMIT's facilities, such as the thermolabs, the group set out to design and implement robust and reliable experiments. Additional testing was to be carried out on computer programs ANSYS and Excel. ANSYS modeling was to be used to compare carrier material types and behaviors. Finite element analysis calculations were to be completed in Excel and used to compare heat flow characteristics. Following the determination of these goals, testing was successfully conducted both physically and theoretically. For the physical tests, a test rig was fabricated using leftover 3D components from a previous capstone project that also tested using a wind tunnel. 2 diffuser sections were combined with a custom-built midsection that included a removable clear acrylic lid. This is so we could conduct an open static test with no airflow and a still dynamic test with air flowing over the system. Both dynamic and static tests used thermocouple wires that were placed in specific areas of the aluminium heat pipe carrier to measure the temperature. These were linked to a data logging machine that collected and plotted data over time and range. A heat source with power restricted to 90 watts by using 7.5 amp and 12 volt inputs was set so the maximum temperature of 120 degrees Celsius could be reached. For the ANSYS model, the iteration developed last semester was modified to better reflect the actual system design and simulations. Similarly, Excel calculations of finite element analysis completed last semester were adapted to better reflect learnings over the second semester. Data gathered from testing was then plotted so that we could derive learnings for our industry partner, Fujikura.
Hello, my name is Sarita and I will cover about the results analysis from the experiments. So according to the results which we have conducted through Excel calculations and sets analysis and physical experiments, we are able to illustrate the flow of the heat through the heat pipe carrier and indicate the significant design parameters of the plastic carrier through these experiments. The results that we obtained, the heat flow along the heat pipe carrier was determined from Excel calculations and ANSYS analysis was continue going in the same direction. This one is a tabular result of the plastic heat pipe carrier and aluminum carrier. with respect to the temperature. And this one is the results from ANSYS analysis in temperature. The first one is the plastic. The second one is the aluminum carrier. And you can see the relationships between the temperatures and the distance. The lower the distance, the higher of the temperature. It shows that aluminum can dissipate the heat better than PVC carrier. However, the physical testing results of aluminum carrier is slightly different from both previous methods. The minimum temperature moderately drops from the maximum temperature. As you can see from the graph that we have mentioned it in methodologies that we attach the thermocouples in total 5 points. This one is the graph demonstrated the static physical testing between the temperature in degrees Celsius and the time in hour per minute. At the maximum temperature was around 120 degrees Celsius that occurs on the heat source, which is a couple block, while the minimum temperature around 103 degrees Celsius is on the carrier point 1, where it's the farthest point from the heat pipe in heat sinks. The temperature on the carrier depends on the distance between the heat pipe and the points, which you can see that the closer the points, it will show the higher temperature. And this one is also the graph that demonstrates the dynamic physical testing results. According to the graph, the temperature data of each point were collected since the static conditions occurred this region. You can see that this region is the static region, and then the temperature were almost stable until the fan was turned on to change the system into the dynamic condition, and slightly stable again at the lower temperature when the time passed around 10 minutes. After 10 minutes passed, the temperature was approximately around 68 degrees Celsius, that's the maximum one, and the lowest one was around 37 degrees Celsius. So overall, the results in the physical testing yield very tiny differences in values compared to Excel computationals and ANSYS analysis, and the physical model agree with our theoretical models. Additionally, the previously described explanation would be supported to the PVC carrier test finding as well, which should show the comparable tendency to the theoretical result. In conclusion, what we have learned to reduce the weight of carrier by utilizing the plastic instead of aluminum, according to the result, the indications of the design parameter takes an important role, which in this case the heat transfer might be improved when we're considering the surface contact between the heat pipe and plastic heat pipe carrier. So the limitations of the plastic could be compensated by increase the surface area contact between the heat pipe and the carrier. And next part, my friend will elaborate more about how we help our industry partner or Fujikura.
Over the course of the year, our group has gained valuable information for our industry partner, Fujikura. Based on the literature review, there is very little information and data for heat pipe carriers specifically. And in conducting a variety of tests, gaps in research have been addressed. For plastic carriers, our group has provided a basic indication of the design parameters that will need to be considered during design and testing phases, with heat loading at certain points and behavior of the heat flow through components shown. Overall, the research paper successfully met our goals set out at the start of the year and can hopefully provide a robust start point for future research on the topic of plastic heat pipe carriers.